All right, so we're talking about linear homogeneous. So we're going to be starting chapter 3, and chapter 3 is higher order ODEs. And so chapter 1 was first order, chapter 2 is second order, chapter 3 is nth order. So we're just going to go as high as possible. So what does it mean to be an nth order ODE? So that means your book's going to use this to represent. So here, if I have y to the fifth, that means the fifth derivative, right? It doesn't mean y is raised to the power of 5, it means the fifth derivative. And so we're going to be looking at linear ones. We're not going to do, we might, I don't remember if we did anything nonlinear. And so here we're just going to say, so an nth order ODE. So this is the highest derivative here is to the n, right? So y to the n plus some pn, some function of x raised to n minus 1, so all the way to the n plus some r of x. And if it's 0, we call this homogeneous. If not, it's non-homogeneous. There's some of this stuff I'm going to eviscerate when I finish writing the other notes when I reteach this class. Notice if this is not, if there is some sort of Pn of x here, you can just divide it out in order to achieve that this has a coefficient of 1. So if this has anything besides that, you can divide that out and get the coefficient of 1. So this is what it means to be nth order. So what we're going to want to have, this is the part where I wish I taught you guys more linear algebra than we did, but I taught you just enough to get by. This is a differential equation class, not the linear algebra class. We're going to be dealing with the general solution basis. And so we're going to have our solution. If it's an nth order, I'm going to need n independent, linearly independent solutions. And here I talk about a little bit about what it means to be linearly independent. And so a set of functions are linearly independent if linearly independent on the interval I, right? If k1 y1 plus k2 y2 is equal to this, where k, these are constants, right? If implies that all of them are 0, we call it linearly independent. And so, however, if there is some combination, any combination where these are not 0, that means one was a multiple or another, or some linear combination of like 1 plus another equals a third, then we can say, well, that's not linearly independent. And let me kind of give you a quick example. So if I have e to the x, that is linearly independent from x cubed, right? So this is independent of this. However, but if I had it, so if I had y1 equal to e to the x, that's linearly independent than y2 equal to x cubed. But let's pretend I had another one of y3 equals 5 e to the x plus 2x cubed. Oops, make that a cube. This is no longer linearly independent. What do I mean by that? It means I can have 5x, and if I plug, and what I mean by that is here is I could say I could have minus 5 y1 minus 2 y2 plus y3 equal to 0. And that means there's some combination where these are non-zero, aka k1 is 5, k2 or negative 5, k2 is negative 2, and k3 in this case would be 1 equal to 0. So these are no longer linearly independent, even though that none of these are multiples of each other. If I take some linear combination of these two, I can achieve this. And so that's what it means to be linearly independent. So we're going to look for things that are kind of fundamentally different. We're going to look for a whole bunch of them, right? And so so for an nth order, we're going to need to find n of them. So we have to find a bunch. Okay. If you've had a linear algebra class, this is very obvious to you. If you haven't had a linear algebra class, this may or may not be as obvious. All right. So how do you determine if it's linearly independent? So your book introduces the Wronskian again. You're going to do 1 or 2 problems from this. Once again, I want you to do this, but I'm not going to test you on the non-scan, as I've said before. You're going to just take this, and so if I have nth order, if I have n of them, right? If I have n solutions, I need to find. You're going to write them all out. So let's just do a quick example of what we have here. So here I have e to the x, I have x cubed, and let me change this. Let's just say it was sine of x. So that way I know they're linear independent, right? So here we'll let this one be y1, y2, and y3. And then here you're just going to take its derivative. Well, this is just e to the x, e to the x, e to the x. This is 3ex squared, and this would be 6x, right? And so you take all the way up to the length of this. Sine goes to cosine x, and this is minus sine of x. So here's just a quick sample of a Wronskian, where if I had y1 equal to e to the x, y2 equals x cubed, and here I'm going to have y3 is equal to sine of x in this case. If the Wronskian is not 0, then the set of functions is linearly dependent. So here you have to, hold on, did I say that right? Hold on. Hold on. I do not trust myself all of a sudden. The first section is one of those introductory sections where we don't do math, we just talk about stuff forever. Which drives me a little bit nutty. I get why they do it, but it's just, I was like, won't we? I don't know. How my brain works is slightly different. Hold on. Let me make sure I wrote that right. Where does it talk about the Wronskian? Solution, linear independence. Uniqueness, Wronskian, right? This the Wronskian. Furthermore, all right, so this would be very just continuous coefficient. Furthermore, if okay, I think it's on x correct. So here we're going to do the Wronskian and do the same thing. So look, it talks about uniqueness and uniqueness. So basically, if the coefficients are continuous in some open interval I, then the initial value probably has a unique solution. So not only does it exist, there's a unique solution. So we're not going to go too in depth in this like we did last time. We're just going to say, as long as these are continuous functions, we're fine. Right? And here we're going to say linear independence. You can use the Wronskian. You're going to solve for a couple of Wronskians just because I want you to get practice of doing derivatives and just putting stuff into this mess and just doing determinants. But you're not going to really see this on your exam. Everything I'm going to hand you is going to be, you're going to get literally independent solutions. You're going to get exactness and uniqueness. Now, I might dance around a little bit to make sure that happens, but we'll make sure it happens. Okay. Yeah. Literally, there's nothing for you really to fill out. If you send me the first page is the first page and don't leave all these marks, I'm fine with it. Right? But this is actually doing 1 or 2 things. All right, so let's do this, and that way I can walk through some of these problems with you. All right. So find the general solution of this mess. And I'm just so old school. I write. If you see Roman numerals, do you guys know that means derivatives? Do you guys know that? So if you see like Roman numerals, if you see like y to the, VII, that's the 7th derivative, right? Your book goes to, this is the more modern way of doing it. Or at least that's what I think is the more modern way of doing it. It's just because before it got kind of messy when you did all that, and so we just used Roman numerals to make it clear, but now with everything being typed, you can just put it in parentheses, looks nice, and everyone's good. All right. So remember that we want this to be linearly. I knew I did this wrong. This is independent. As long as it's not 0, it's linearly independent. Sorry. I knew I would make a mistake there. I was like, this doesn't look right. Independent. I guess if I said if it was 0 is dependent, but that's not as clear. You got to be careful what you say in math. If it is 0, I know if it's not 0, it's independent, but I don't know if but you cannot just say the opposite, right? I can't just say if it is 0, it is dependent. I haven't proved that yet, at least in my mind. It might be very true. I just haven't proved it. So let's do this real quick. So how am I going to do this? Well, we're going to do this the same thing the way we've done all this. So if I have this, what am I going to do? I'm going to guess the same thing I guessed before when I had this. I'm going to guess e to the lambda x. So if I make that guess, right? Why would I guess that? Because then here I have always e to whatever lambda x and with a bunch of coefficients on it. And so they should cancel each other out, or at least there should be some way to do it. So here I have e to the lambda x, and then here if I put this in, what do I have here? I have lambda to the fourth, right? Because I have the fourth derivative, so that would pop out 4 times, minus 5 lambda squared plus 4 equal to 0. And so this is my characteristic. So we're going to solve it the same way. I'm going to rebuild this for you, but I'm just using this now as a placeholder. So here we have our characteristic equation. Since this can't be 0, this must be 0. So what are my lambdas? Well, my lambdas here are minus 2, minus 1, 1, and 2. How did I do that? Well, it's easy. I just factor, and I get plus or minus. I get minus 4 and minus 1, and then I take the square root, and so it's plus or minus 1 and plus or minus 2. Or you could just chunk it through a calculator. Let's be honest, that's what you guys are going to do. So here I have y is equal to c1 e to the minus 2x plus c2 e to the minus x plus c3 e to the x plus c4 e to the 2x. Okay, so remember each one of these lambdas is a solution. Here I get 4 unique solutions. Is that what I'm looking for? Yeah, it's the 4th order. What about 7 dots? I haven't seen the 7 dots recently. So, all right, so let's look at this. All right, so let's look at the Wronskian of all this math. So what are my solutions here? My solutions here, my Wronskian is equal to the determinant of e to the minus 2x, that's one of them, e to the minus x, e to the x, and e to the 2x. So these are my 4 solutions, right? 1, 2, 3, 4. That's my 4 independent, what I assume to be linearly independent. I'm going to prove it to you. So we're going to take its derivative. So this is minus 2 e to the minus 2x. This becomes 4 e to the minus 2x. This will be minus 8 e to the minus 2x. We'll take the derivatives here. So I get minus e to the minus x. I'll get e to the minus x. I get e to the minus x. Here we'll get e to the x, e to the x, e to the x. What do we have here? We'll have 2 e to the 2x, 4 e to the 2x, and we'll have 8 e to the 2x. All right, so we have this. So how am I going to take this determinant? Well, here we're just going to set x equal to 0. We're just going to find it for a point, right? We just need it to be 1. So if we set x equals 0, all we're looking at is coefficients here. So 1, 1, 1, 1, minus 2, minus 1, 1, 2, 4, 1, 1, 4, minus 8, minus 1, 1, 8. Okay. And if I crunch this through a calculator, it's 72. And so we say this is linearly independent. And so we use the Wronskian to prove that these are linearly independent. Okay. And so what you do, you just set them all, you just set all your answers up in this, take its derivatives, so you don't take n derivatives. So if I have 4 answers, I'm going to take 3 derivatives below it. So n minus 1. You pick a value of x, which makes your life easy, plug it in, and see what you get, and show that this is non-zero. Okay? So that's 72. Yeah, that's 72. I crunch through what that is, should be 72. All right. So let's do another problem. So real quick in chat, if I saw this, what would I probably guess my solution was? What does this look like? What does this look a lot like? See if you guys vaguely remember. I know, that was like a week and a half ago, Professor. Come on now. You can't expect us to do any of this. Kashi, yeah. Euler Kashi. This looks a lot like Euler Kashi. Did Euler Kashi really care that we only did it really didn't matter how big it is, right? Because here, if I keep adding x's and getting rid of my derivatives, I'm going to guess my solution looks like x to the m, some x to the m, right? Because this will be 3 lower, but I'm going to add that back in by adding x cubed. This is going to be 2 lower, but I'm going to add that with the x squared. This is going to be 1 lower, and this is going to have that back with the x, and this is just going to be that. So this will all have the same form. And so if we make this guess, and this is our guess, we can produce a solution. So if I take its third derivative, I'll have m minus 1, m minus 2, x to the m minus 3 times x to the m minus 3 times x to the 3. So this is just m. I'm just going to cut to the chase. It'll be minus 3, and then we'll have m minus 1, x to the m plus 6, m, x to the m minus 6, x to the m equals to 0. We factor all this out. I'm going to get x to the m. There's a lot of math here. I'm just going to skip it just for brevity's sake. X cubed minus 6m squared minus 11 or plus 11m minus 6 equals 0. Well, can x to the m equal to 0? No, right? So we need this to be equal to 0. So we just set that equal to 0. And this actually factors quite nicely. We'll get m equal to 1, 2, and 3. This is one of those highly contrived problems, just so you know. So here we have our solution of y equals c1x plus c2x squared plus c3x cubed. All right, so how are we going to solve the initial value problem? Well, we get to our general solution like we did before, and then we're going to plug in x. We're just going to plug these in. And so let's just do that real quick. So he'll have y of 1 is equal to c1 times x to the 1 will just be c1 plus x squared. So this is plus c2 plus x cubed to plug in 1 would be c3. So I have c1 equals, so I have, oops, and that's all equal to what? 2. So this all equals 2. So c1 plus c2 plus c3 equals to 2. Y prime of 1, so here we're going to take its derivative. So this becomes c1. Here I'll get 2c2. 2c2 times x. Well, if I plug in 1 for x, I'm just going to get 1. I'll get 3c3 with x squared. But if I plug in 1, I'll just get 1. And that's equal to 1. And then here I'll do y double prime of 4. Oh, no, y double prime of 1 is equal to minus 4. So what do I have here? Well, I don't. Well, if I took its double derivative here, I get nothing. I'm going to have 2c2 still. I'm going to have 6c3, and that's going to equal to minus 4. So what do I have here? I have a system of 3 unknowns, c1, c2, c3, with three equations. And so what I do, I just chuck it through a linear algebra system, right? So you just put it in an augmented matrix, hit RREF, and you're going to pump out these answers. C1 is equal to 2, C2 is equal to 1, and C3 is equal to minus 1. Once again, why would they teach linear algebra later when you need it to answer that? I don't know. I just don't know. I really want to email the book guys. It's like, do you just assume that they've had linear algebra before this? But then why do you teach it? And why is it not up front? I don't know. And so here's our solution. So here's our solution to our initial value problem. Okay, so that's the end of the first section. I'll leave that up for a second. We'll bring up the next set and go from there.